Welcome to the deep dive. Okay, so you listeners have sent in some really great stuff about how we learn math. We've got some interesting sources.
We certainly have.
And today we're going to plunge into one particularly solid piece of research. It's a meta-analysis looking at worked examples.
Right.
How they affect performance in math.
Right.
The big question, really, is what are the most effective ways, the best ways to grasp and, master mathematical ideas?
Exactly. And this study you pointed out is from the Educational Psychology Review, a meta-analysis of the worked examples effect on mathematics performance. It's a fantastic starting point.
Why is that? What makes it stand out?
Well, it's the scope. It's just huge. They didn't just look at one or two studies, right? They synthesized findings from tons of them.
How many are we talking?
They actually reviewed, get this, over 8,000 abstracts.
Wow. 8,000.
Yeah. To find the really rigorous work, they ended up focusing on 55 specific studies. And these covered learners from elementary school all the way up through university.
So a really broad range then.
A very broad picture, yeah.
Okay, so just to be crystal clear for everyone listening, this isn't just like one person's theory or a single classroom experiment.
Not at all.
Our mission here in this deep dive is to pull out the key insights from this massive pile of research. What makes learning math from examples work? And maybe just as key, what doesn't work, quite like we thought.
Precisely. And just so we're all on the same page, when we say worked examples, what are we talking about?
Good point.
We mean those step-by-step demonstrations, the kind you see in textbooks where they show a problem and then walk you through every single step to get the answer.
Got it. Step-by-step solutions laid out. Okay, groundwork done. So what's the headline, the big takeaway from all this research?
Well, the main finding, boiling it all down, is that worked examples generally have a medium positive effect on math performance.
Medium positive. Can you quantify that a bit?
Yeah, they calculated an average effect size, G equals 0.48.
0.48, okay.
And that was statistically significant, p-value of 0.01. So in research speak, that's pretty solid evidence. Studying worked examples generally seems to help people get better at math.
A medium positive effect across all those different levels and topics. That's quite encouraging, isn't it?
It is.
So for you listening, if you're looking for ways to maybe get knowledge quicker, but still thoroughly, paying attention to good worked examples looked like a pretty decent bet.
Absolutely. But, like always, the devil's in the details. Or maybe the interest is in the detail.
Yeah. The nuance.
Exactly. The researchers didn't just stop there. They dug deeper. They wanted to know what makes these examples more effective, or maybe less effective sometimes.
Okay, so moderators. Things that change the effect.
Right. And one key thing they looked at was the type of example used.
Okay. Now, this is where I get really curious. What kinds of examples did they compare?
They mainly looked at three groups. Studies using only correct examples, studies using only incorrect examples, maybe showing common mistakes.
Right, like learning from errors.
And studies that used a mix, so both correct and incorrect examples together.
What did they find? Which worked best?
The results were pretty striking, actually. The studies using only correct examples, they showed significantly bigger positive effects on learning.
Bigger than using incorrect ones or bigger than using the mix?
Bigger than both, compared to using only incorrect examples or using the combination of correct and incorrect.
So wait, even though we hear a lot about learning from mistakes, this huge analysis suggests that for worked examples in math, just seeing the right way clearly from the start is actually better.
According to this meta-analysis, yes. When you're using worked examples specifically, focusing on the correct pathways seems most beneficial, especially compared to only looking at errors or even a mix.
That kind of makes intuitive sense for building that first understanding, doesn't it? You want the blueprint before you start analyzing why the other building fell down.
That's a good analogy. It helps build that accurate mental model first. Now, here's the finding that might really make people pause.
Okay, I'm ready.
They also looked at pairing worked examples with self-explanation prompts.
Right. Asking the learner to explain the steps to themselves, like why did they do that?
Exactly. And that's usually considered a really powerful learning technique, right? Deepens understanding.
Definitely. So what happened when they combined them? Surely that boosted the effect.
Surprisingly, no. The meta-analysis found that adding self-explanation prompts actually negatively moderated the effect.
Negatively? You mean it made the worked examples less effective?
That's what the data across these studies suggested. Worked examples without the prompts were, on average, more effective for improving math performance than the ones with the prompts.
Well, hold on. That feels completely backwards. Why? I mean,
Uh,
everything we read says active processing, explaining it yourself. That's key. This
oh,
is,
Right.
yeah, this is a real aha moment, maybe challenging a core assumption here.
It certainly challenges it in this context. And the authors, they acknowledge it seems odd compared to some learning
So
theories.
what's the thinking? Why might that happen?
Their interpretation kind of leans towards cognitive load. The idea is maybe asking learners to generate explanations while they're also trying to understand a potentially complex new procedure from the example. Maybe it just asks too much of their working memory at once.
Ah, cognitive overload. So
Yeah.
you're trying to follow the steps and articulate the reasoning simultaneously. And that's just
right.
too much mental juggling, especially at the beginning.
Potentially, yes. Especially when you're first grappling with it. It could be that just focusing purely on absorbing the correct steps from the example is initially more efficient for the brain.
So less is more,
Yeah.
perhaps, in that initial phase. Get the how down solid before you push yourself on the why.
That seems to be a plausible takeaway from this research, yeah. It suggests that specific combo worked examples plus self-explanation prompts might not be the universal booster shot for math learning we often think it is.
Wow. Okay. That is genuinely fascinating. I really would have put money on self-explanation being a net positive always. Okay, what else did they look at when you use the examples? Like, does timing make a difference?
They did. They checked if the effect changed depending on whether the examples were used for, say, initial skill acquisition, first time seeing a concept, or used later for practice and reinforcement.
Did it matter?
Their analysis showed the positive effect pretty much held up in both scenarios.
Oh, interesting. So it's not just a tool for absolute beginners when they're lost.
Apparently not.
You can still benefit from reviewing worked examples even when you're, further along doing practice problems.
Exactly. They can still be a really valuable reference, a way to check your work, reinforce the correct method, maybe spot where you went wrong without having to, reinvent the wheel every time.
That's actually really practical.
Hmm.
Because sometimes you feel like, okay, practice time, I should just struggle through it alone. But maybe strategically looking back at a worked example is actually a smart move.
It seems it can be, yes.
Okay, so this all ties back to how our brains learn, obviously.
Mhm.
Did they connect it much to broader learning theories? You mentioned cognitive load.
They did, yeah, mostly implicitly through the findings aligning with cognitive load theory. They didn't dive super deep into the theory itself in the paper, but the results fit.
Right.
The basic idea being our working memory is limited, right?
Huh?
Try to cram too much in at once, learning suffers. So a well-designed worked example, especially a correct one, can lower that mental effort. It gives you a clear path.
Reduces the cognitive load.
Exactly. Frees up some mental bandwidth to actually understand the concepts, not just juggle the steps.
And that finding about self-explanation, potentially adding load, fits right into that framework too.
Mm.
Trying to do both at once might just max out your capacity, especially early on.
Precisely. Focusing first on a clear, correct example lets you build that foundation without overwhelming the system. It's about managing those cognitive resources effectively.
Okay. This has been incredibly insightful. Let's try and crystallize this for everyone listening. We've gone through this big meta-analysis. What are the absolute key takeaways? If someone wants to learn math better using examples, what should they remember?
Okay, first, big picture. Worked examples generally help. They have a decent positive impact on math performance across different levels, so they're a worthwhile tool.
Good. Number one, use them.
Number two, the type matters a lot. Prioritize learning from clear, correct examples. This research suggests that's more effective than focusing on incorrect ones, or even a mix, at least initially.
Okay. Focus on the right way first. Got it.
Third, the surprise finding. That common advice about always using self-explanation prompts with worked examples. It wasn't supported here. In fact, it seemed to sometimes make them less effective. Maybe hold off on demanding self-explanation right at the very start.
Right. Counterintuitive, but important. Less might be more initially. And
Fourth, timing isn't a huge barrier. Worked examples aren't just for day one. They're useful for initial learning and for practice and review later on.
okay, great summary. So let's turn this back to you, the listener. A final thought to chew on. Given these findings, how might you tweak your own math study habits? Or how you help someone else learn math?
Yeah, should you maybe actively look for more clear, correct worked examples when you hit a tricky spot?
And maybe pause before automatically pushing for that self-explanation the moment you or someone else looks at an example. Should you let the correct process sink in first?
It really gives you something practical to consider, doesn't it? How to potentially optimize that learning process using examples more effectively.
Absolutely. Some really compelling food for thought there from this deep dive into the research.
Definitely. There's always more to uncover about how we learn, and hopefully these insights give you something useful for your own journey with math.
Thanks for joining us for this deep dive. We hope it sparked some ideas. Until next time.